Hello, geometry scholars. Mr. Benzel here, and we are moving into the next unit, which is sort of how to think like a geometer and kind of build into a very logical, competitive real-world thinker. So our skill 2.1 is on conditional statements, which is really about developing good definitions and rules in geometry. All right, so I want to kind of give a little motivation for the first example here. Those of you who have me or know of me here in high school know that I have a 4-year-old named Alice, and that my wife, Mrs. Benzel, teaches music at here in high school. And Alice is taking violin lessons, and part of the way that Mrs. Benzel motivates Alice to practice her violin in the morning is that if she practices the violin as asked, then she can have her movie time in the afternoon. So when everybody goes home and you guys are going home and relaxing, Alice is watching the movie Paw Patrol in the afternoon when we get home from school, just to kind of unwind, and she gets, cozy on the couch and enjoys an afternoon movie at the end of the day after school. So she is successful at practicing the violin because we have a conditional statement for her, which we basically tell her, if Alice practices the violin, then Alice can watch Paw Patrol. So there's really two parts of a conditional statement. The red part is the hypothesis, so we call this the P part. So the P part is Alice practices the violin. So the only way that this rule works, we assume this to be true, we assume that Alice practices the violin. And then the conclusion is the result of practicing the violin, and that's why it's called the conclusion. So that's the blue part. So the conclusion is that Alice can watch Paw Patrol. Now, one of the things that we actually do, when we write conditional statements is we write it in a notation, like in symbols, to kind of help us develop. So you'll actually see us write in symbols first. A lot of students actually do well with the symbols, and it helps them create their conditional statement. So the notation is P arrow Q, so we could actually translate this into if P, then Q. And then we could just substitute, if Alice practices the violin, then Alice can watch Paw Patrol. So this is just your basic conditional statement. And we're actually going to kind of develop some other types of conditional statements by using our symbols. So let's take a look here. So the first type of conditional statement that we have is just the straightforward conditional. So remember, I'm just going to kind of write for reference here that the P part is Alice practices the violin. And then the Q part is that Alice watches Paw Patrol. Okay, so let's actually build these conditional statements. So the first one is pretty obvious here because we already have created it. So this is our P arrow Q. So this would be if Alice practices the violin, then Alice watches Paw Patrol. The converse is just flipping the order of the Q and the P. So the converse, we actually always write in the form of Q arrow P. So this would read, if Alice watches Paw Patrol, then Alice practices the violin. And then the inverse, this is where we negate. So this would be not P, arrow, not Q. So note that this symbol means not. So if Alice, so the opposite of practicing the violin is doing what we don't want her to do. So this would be if Alice doesn't practice the violin, then Alice does not watch Paw Patrol. And then the contrapositive, this is where you're doing the converse of the inverse. So this would be not Q, arrow, not P. So if Alice doesn't watch Paw Patrol, then Alice doesn't practice the violin. So basically, the purpose of these is that we can kind of like flip the order, and we can actually assess the quality of a definition by determining, whether the conditional is true, the converse is true, and so on. All right. So a note about true and falsehood, we can evaluate conditional statements as true or false. So especially when we kind of look at the more mathematical ones, where we're kind of evaluating the geometric definitions, I am going to ask you to look at whether the statement is true or false. All right, so now what we're going to do is we're going to look at a geometric example. So this is a definition, that's right out of a geometry book. So this is something that we studied in the last unit, supplementary angles. So supplementary angles are two angles whose sum is 180 degrees. So what we want to do here is we want to write it into if-then form. So what I'm going to do is I'm going to first call the P part two angles are supplementary. And then the Q part is the angles add to 180 degrees. So you may write sum is 180 degrees, but you want to kind of make sure you kind of have a noun in there to make it grammatically correct. We could say the angles add to 180 degrees. And I'm just going to kind of make that shorthand. So now I can write it into if-then form. So if two angles are supplementary, then the angle sum is 180 degrees. And obviously, that's true, because when we were taking our test last week, well, doing the delta math IP about, supplementary and complementary, when you see the word supplementary, you want to make sure that you are adding those angles to 180 degrees. All right. Now we're going to kind of look at the converse and the inverse and the contrapositive. So we could say for the converse, this would be your Q arrow P. So P is the two angles are supplementary. And then the Q is that the two angles add to 180 degrees. So like from the converse, we could say if the two angles add to 180 degrees, then the two angles are supplementary. And that is true, because supplementary describes, two angles that add to 180 degrees. All right, now let's look at the inverse. So the inverse is not P arrow, not Q. So if the two angles are not supplementary, then the two angles do not add to 180 degrees. And that is also true. So obviously, like if they add to 90, we can't call them supplementary, or if they add to like 145. And then the contrapositive would be not Q arrow, not P. So this would be if the two angles don't add to 180 degrees, then the two angles are not supplementary. And that is true. Okay, so make sure you kind of have the converse, inverse, and contrapositive down for these. You may want to pause the video. It is a little bit of writing, but you can pause, write it down, take a screenshot, take notes on it. So now we're going to kind of look at the notion of a biconditional statement. So we see here that we got trues, no matter what direction. So this tells us that we actually have a very good, well worked out definition. So actually this is a biconditional statement in itself, because I have the term if and only if. So this means that it works both ways. So what this means is that if the conditional statement is true and the converse statement is true, I could write a biconditional statement. And the notation for that is actually an arrow that is both ways. So instead of writing both the conditional and the converse, I could say that two angles are supplementary. if and only if they add to 180 degrees. So we do have to see that both the conditional statement is true and the converse. So let's actually take a look at a one that doesn't work out as well, and we can kind of see what happens. All right, so here's a biconditional that does not work. So what we would do here is we would write this as a conditional. So we could say if angles are a linear pair, and I'm kind of making this like grammatically correct, then the angles are supplementary. So let's kind of evaluate that for whether that's true or false. So I'm just going to draw a linear pair and note that supplementary means, and I'm just going to kind of make a thought crowd here for what your thinking should look like, that they add to 180 degrees, and that is true. So far, so good. Now, let's look at the converse. So this would be if the angles are supplementary, then the angles are a linear pair. And let's actually draw this. So I like to kind of think about when I'm looking at true or false, can I actually prove this statement wrong? So obviously, linear pairs are supplementary, so that works. But I could also draw, something that looks like this. So maybe like 120 and a 60 degrees. So these are not linear pairs. So this means that you cannot write in a biconditional statement. Well, I mean, you can, but it would just not be true. So the statement that with an if and only if, we would say that the biconditional if and only if statement is not true. So we would say that like P arrow in both directions is not true. You cannot write a biconditional statement. Okay, so, and kind of a good explanation is you could just say the converse of the conditional statement are false, or you could even show me an example for where it is wrong. But to show me that a biconditional is true, you want to write that both the conditional and the converse are true. So I'm just going to kind of write that as a reminder here at the end. So note, to argue that a biconditional is true, write both the conditional and the converse are true. And if you kind of mention the conditional and the converse in your explanation, that is gold mine for exactly what we are looking for. So with that, if you get good at conditional statements and know your vocabulary, then geometry will be a much more pleasant and manageable experience for you. And you may even find that tasks like writing proofs will actually be a lot easier for you too. So stay tuned.